Hi, my name is Matthew Castronuovo, and this is my Physics Lab 2, the motion of a falling object. So, introduction, the purpose of this lab is to observe the motion of a falling object that is falling vertically. Some important concepts include Newton's first law, kinematics, an equation that will help us in our iterative process that relates the acceleration, velocity, initial, and position initial to help us find and predict the final position. Velocity update formula, which again will help us in our iterative process to update where we are observing the object or how fast we're observing the object to be given a constant acceleration. And then position update formula, which does the same thing as velocity update, but with position. And then the force of air and drag resistance, or air resistance and drag, we observe that and we watch its effects. So the main results of the lab are shown on the graph to the right, where we have our data in blue and then two computational models. The first model being in yellow, which discounts the force of drag, and the second model in gray, which tries to account for the force of drag. So the experiment, the surroundings, well, first of all, the system is just the black eraser that I used. I dropped it. And then the system or the surroundings is everything else, that being the air, that being the basically anything that's just going to come into contact with the eraser, which for all intents and purposes is just the air. So the initial conditions is the eraser the second it's been let go, where no forces are acting on it besides gravity and drag. It is at rest, and in that moment is at rest. And some experiment details, I simply just dropped an eraser and then went onto Tracker and tracked its trajectory and positions over each frame. So some assumptions in the models that I created. For the first model, I assumed that there's no air resistance work on the eraser. And how did I show this? Well, B is equal to 0. B is the constant in the drag equation, B times the speed squared. So setting B equals 0 sets the force of drag equal to 0, which is how our first model works. Now, the second model, the drag forces working on the eraser is going to be always given by the equation. The force of drag is equal to the constant B times the magnitude of velocity squared. And the model assumption for both is that there's no human error in the data collection. So these are my two models, the one on the left being without drag, where you can see B equals 0, and the one on the right being with drag, with B being equal to 0.0181. How did I obtain this value? I simply did some trial and error until my model predicted the same final position as my data. So what's the key difference? Well, the key difference is that B is not 0, it's equal to some value, which means that we're trying to account for some form of the force of drag. So here's my position time graph, where you can see that the blue is our actual data. Our yellow, which does not account for the force of drag, underpredicts the position, or rather overpredicts the change in position of the eraser. It thinks that it will be moving farther down than it actually ends. And our second model in gray underpredicts the change, or overpredicts the change in position throughout the middle of the trajectory, but in the end is able to correctly predict the final position. So what does this mean? Well, first of all, does our model predict terminal velocity? Terminal velocity is simply the velocity that a falling object will reach where it does not change. It's a constant velocity. So how does it reach this? Well, net force is equal to 0, which means that the force of drag and force of gravity are equal to each other. And we can see this is actually predicted in our second model, because there's a point where velocity is going to be so large, it's increasing due to the force of gravity, but it's going to become large enough that it balances out our force of gravity, and then velocity is not updated because the net force is going to equal to 0. So what if our ball is thrown with a non-zero velocity? Does it still reach that same terminal velocity? Well, the answer is no. And we know this because I actually tested it in the model, where the first to the left you see our original model, and to the right you can see setting the initial velocity equal to -1 yields a different velocity time curve with a new terminal velocity, which is actually just equal to 1. So interestingly enough, if you throw the ball with a speed, it will not have the same terminal velocity.